Photoelectron Spectroscopy. It's another way to study electrons in an atom. Dalton determined that all matter contains atoms, and Thomson went on to find that there are electrons in all atoms. He was followed by Rutherford, who is credited with discovering the nuclear atom. Remember the gold foil experiment? And Bohr followed Rutherford, and Bohr was able to determine that the electrons had different energies and they traveled in orbitals. You might remember electron energies. Sometimes we can call this binding energy, for at least our course, energies. And remember sodium took 495. These are all in kilojoules per mole of atoms, and kilojoules per mole of atoms. We found that it took much more energy to remove the second electron from sodium, and we use this to kind of verify how many valence electrons were in our different elements until we got to the core. So we're going to probe further into the atom, and we're going to look at different types of electromagnetic radiation. You might remember our equation from Planck's constant times frequency gives us energy, and these different energies affect the atom and molecules in different ways. So if we first look at the longest wavelength, it's microwaves, and they use microwaves for studying the rotation of molecules as well as the shape of molecules. So I have a couple of examples for you. So think about a water molecule rotating on different axes. They can study that rotation using microwaves. Notice the energy of the microwaves is expressed in mJ per mole, which is megajoules per mole. If we use a shorter wavelength, so it'll have a higher frequency, infrared, you know it as heat, will make the molecule vibrate. Molecular vibrations is when the length of the bond changes. So you can see that they use it kind of like springs. So you have a different length of the bonds. Visible light, this is what causes our hydrogen bright light spectra. And these are your valence electrons transitioning to a higher energy level and falling back down. So we have the different wavelengths for hydrogen. Remember, wavelength is related to frequency. Frequency is that nu symbol, and it's the speed of light divided by lambda. This is an equation on your AP sheet, so you might want to review that a little bit. If we use just the other diagram, you might remember as you add different energies to the hydrogen electron, we get different transitions. So if it goes from the first energy level to a higher one, we call it the Lyman series. And I actually explained it as it was falling back down. Notice that would have the highest energies. So this would be UV light. Our middle is the Balmer series. This would be visible light. And this last one, the Passion series, is actually an infrared light. X-rays are used for core electron transitions. So thinking about the core electrons, those are not the valence, so they're the inner shells. This diagram uses a style, instead of saying the first energy level, they use K, second is L, third energy level is M. Notice the electron that is being emitted or ejected is an inner electron. So that's what we're going to study with photoelectron spectroscopy. So when you're removing those core electrons, okay, again, the core electrons are not the valence electrons. It takes a lot of energy. They're right near the nucleus. They're held on very tightly by that nucleus. So if you have enough energy in your light to remove a core electron, it's going to remove all the other electrons as well. So as you read through this definition, it says any frequency of light that's sufficient to remove electrons from the first shell, remember that's your core, can remove electrons from any of the other shells. So core electrons are anything but the valence. So they're just not the valence. So if you look at the numbers, we have the energy needed to remove electrons in the first energy level is 103 megajoules per mole. Look at how much less it takes to remove the electrons from the second energy level. So that's kind of the premise behind this. Photoelectron spectroscopy, abbreviated PES, measures the kinetic energies of the ejected electrons. So the incoming energy is X-rays, and it's a known quantity. By measuring the kinetic energy of the electrons, the binding energy of those electrons can be determined. The machine looks something like this. Notice it's a nice basement. And the actual machine, the schematic shows you first you have some X-rays from some source. It hits your material. When it's the right energy, it will eject your electrons, so they call them photoelectrons. The detector receives the electrons and detects the kinetic energy. So it says analyzer for kinetic energies up at the top. And we produce this spectra. And our goal today is to understand that spectra as well. So that spectra is called the photoelectron spectra. Some things that are special about it. One, the smallest end is on the right side. So your smallest number is to the right, which is different for us. Notice the vertical axis is number of electrons. So it doesn't really mean 2 electrons, but it's a relative amount. Along the bottom, your x-axis, megajoules per mole, or it could be the binding energy. You might see some type of energy down there. Now, with this spectra, it tells us the element is 4, so it's magnesium. So to help you understand it, let's first write the electron configuration for magnesium. Magnesium has 12 electrons. If you haven't done this for a while, grab a periodic table and play along. So 1s2, 2s2, 2p6, 3s2. So you might remember 2 valence electrons. Now I want to draw it a different way with the orbital notation. Remember the 1s was the easiest to fill. This is like your off-bow principle, which is shown here, but a little bit more visible here. And then we have the 2s takes a little bit more energy. The 3p, a little bit more than the 2s. And then in magnesium, we have a 3s, and that's even more energy than the 2p. So along this axis, we just have some energy. So thinking about this X-ray coming in with a certain amount of energy, the easiest electrons to remove are the 3s electrons. So when you look at this spectra, these guys are your 3s electrons. And I'm going to write 3s2. When you look at the next guy, those are your 2p electrons. Notice it's 3 times as high as your S2, and so it indicates that you have 6 electrons in it. The 2s is just a little bit down, a little bit less energy than your 2p's, and that is 2s2. And the one that comes first, those are your core electrons at 1s2. Note that that's 100 megajoules per mole, whereas the 3s electrons are less than 1 megajoule. So, helps you identify elements, helps you understand how many electrons are in different energy levels, these photoelectron spectra. So, a little bit more about how this works and how we analyze it. So we have the X-ray source up in the corner. to the left. The analyzer is up at the top. So the ray comes down. Remember, it can penetrate all the way down to your core electrons. And let me try to hit one. And that electron can be ejected and picked up by the analyzer. Of course, it's happening to zillions of atoms. Now, notice which element this is. If it has 3 protons, you have the element lithium. And I like to write its configuration, 1s2, 2s1. So, looking at the photoelectron spectra, easy to remove the first electron in the second energy level. So notice that is your 2s1 electron. And to the far left, that's your 1s2. You have twice as many electrons in the far left than you have in the right. So there's your photoelectron spectra for lithium. This time, we have the element with 5 protons in it. So if you have 5 protons, you have boron. So 1s2, 2s2, 2p1. So your 1s electrons are held even more tightly because you have a greater nuclear charge. So on this guy, we have the lithium spectra first. And now notice with boron, I tend to start on the left. There's my 1s2. Notice it's 19.3. It's much greater than the energy needed to remove the 1s electrons from the lithium. Then way down here, 1.36, that's your 2s2 electrons. Notice that the height of the peak is the same to indicate 2. And your next one is 2p1. It is half as tall as the other peaks, indicating you have half as many electrons. So the photoelectron spectra, let's look at this guy. And I think I have some questions to go with that. Which of the following elements might this spectrum represent? So without even looking at the choices, let's just analyze it. So the highest is down here. Notice we have relative number of electrons. I think that's a better way of putting it than 1, 2, 3, 4. So notice it goes up about 2 lines. So that's got to be your 1s. And they have 2 electrons. So after the 1s, you have 2s. It's about the same height, so it's 2s2. The 4.7 is the kilojoules per mole, the binding energy, so much easier to remove. And now looking at the next one, if you look at the lines, we have 2, 4, 6 lines, so that should be 2p6. And the element that has that configuration would be neon. Our next configuration says give the spectrum above, identify the element and its electron configuration. So like I did, I like to just do it right away. Again, we have the lines to indicate relative numbers. So 1s2 will be our beginning, and then we'll go to 2s2. It's the same height as the 1s2. The 12.1 is the binding energy. Much easier to remove those electrons. Our line is 6 up, so that's going to indicate 2p6. And then we know that it goes to 3s2, and we only have 1 in the next orbital, so 3p1. And that element, yes, I need a little time, is aluminum, because we have 13, or if you look at your periodic table and do the configuration yourself. Our next question asks, which element could be represented by the complete PES spectrum below? Okay, so again, we have relative number of electrons on the vertical, binding energy on the horizontal. This time, my far left is my 1s, the most difficult ones to remove. Remember, you have the highest number to the left. And notice now 4 lines indicates 2 electrons. So next I have 2s2. because I have 4 lines. And my next one, I have 6 lines. So that would be 2p3. And I think I have a little multiple choice. So thinking about your electron configuration, 1s2, 2s2, 2p3, and that is the configuration for nitrogen. Kind of fun, huh? Okay, so which of the following best explains the relative positioning and intensity of the 2s peaks in the following spectra? So what do we have? We have lithium, so they're both identified here, and we're looking at the 2s peak. So I want to think about the configuration for lithium is 1s2, 2s1. Beryllium, 1s2, 2s2. Beryllium is atomic number 4. Lithium is atomic number 3. Let's see what our explanation choices are. Part A, beryllium has a greater nuclear charge than lithium. That's true, and more electrons in the 2s. Beryllium electrons experience greater electron-electron repulsion than the Li electrons. Not true. Lithium has a greater pull right there. Not true, because lithium has less of a pull. And Li has greater electron shielding by the 1s. Not true, they have the same shielding because they're both 1s. So your correct answer is A.